Okay, so in the last video we started our journey through dynamics of systems of particles, developing the center of mass and linear momentum. This time around we're going to take a look at angular momentum and kinetic energy. So let's go ahead and define angular momentum. So just an analogy to everything we've done so far, we'll say that we'll define the angular momentum of the system to be some I equals 1 to n. Basically the angular momentum of the individual particles, Ri cross Mi Vi, like so. And we can observe that that is also the same as some 1 to n of Ri cross Pi. All right. So with that thought, let's go ahead and find the L dot. So we'll go ahead and find L dot here. And I'll suppress the equals 1 to n and just say sum over I. So if I differentiate this, product rule is going to give me two terms. The first one here, when I differentiate Ri, that's just going to give me Vi cross Mi Vi. Oops, M is clearly not a vector. And this is 0 because anything crossed with itself is 0 because that's two vectors pointing the same way. So anything that's parallel or anti-parallel crosses out to 0. And this leaves us with sum over I, Ri cross Mi, and then the time derivative of Vi is going to be Ai. Okay, but we've been here before with that. So sum over I, Ri, this MIAI by Newton's second law will be, so we'll cross Ri into the sum of the external forces on I, plus we have the internal forces, so sum over J, Fi, J, and that sum is buried in this sum here. So we can go ahead and we'll expand, we'll distribute the cross product out. Sum over I, Ri cross Fi, plus now we go sum over I, sum over J, Ri cross Fi, J. And we'll go ahead and do that same dummy index summation trick, except this time it's not going to immediately drop to 0. Okay. So at the moment we're just looking at this term here, and we'll just go ahead and call this guy double star there for later. Okay. So we have sum over I, sum over J, Ri cross Fij. Well, that'll be equal to, and we'll go ahead and again do our split on the indices here. Sum I, sum J, Ri cross Fij, plus, and we're just going to have the relabeled indices here. So sum J, sum I, Rj cross Fji, like so. And by Newton's third law, if I want to go ahead and I can go ahead and rewrite this as minus Fij, so I will. So 1/2 sum I, sum j, Ri cross Fij minus sum j, sum I, Rj cross Fij, like so. And again, the order of summation can be swapped because addition commutes. So 1/2 sum I, sum j, Ri cross Fij minus sum I, sum j, Rj cross Fij. Alrighty then. Now what we can do here is we can pull out the cross Fij part through the subtraction. So we'll do that. So give me 1/2 sum I, sum j of Ri minus Rj crossed into Fij. All right, so now I need to go and take a look at my two particles here. So let's say this is my origin right here. This is my Mi, that's my Mj up there. So then this would be Ri, and that would be Rj. And so then this would be Rij, which is Rj minus Ri. Or sorry, Ri minus Rj. So I can rewrite this as 1/2 sum I, sum j, Rij cross Fij. All right, so this is as far as we can take it for a general force. For general force, that would be obeying the weak version of Newton's third law. And in that case, we can't be assured that the forces are collinear, which means that they could be, say, pointed like that, and that would be totally fine. But then that would mean that Rij and Fij are not collinear. So in general, this term is not equal to 0. So if you've got magnetic forces or something like that, you may find yourself stuck. However, if the forces are central, so if we say if, and this is our big if, Fij obey the strong version of Newton's third law, then that means that either Rij or Fij are either parallel or anti-parallel. And then we can say that the double sum, sum I, sum j, Ri cross Fij equals 0. But that's only if it obeys the strong version of Newton's third law. And so we'll go ahead and assume it does. Since many of our forces are central. In that case, double star will become L dot equals sum I equals 1 to n Ri cross Fi. And that would be, we identified that as the total torque. So we can only get away with that if the internal forces obey the strong version of Newton's third law. Fortunately, they often do. So for an isolated system, the external torque would be 0, and then the angular momentum would be a constant. So so that's the principle of conservation of angular momentum. And our corollary to this is that for central internal forces, only the external forces can change L. All right, so let's go back to our definition of L and see what else we can find. So here it's going to be helpful. Let's say the center of mass of my system is located here. So its position vector would be RCM. And then let's say particle number I is out over here somewhere. And then just following your book's notation, we'll call this Ri prime. So that's the position as measured with respect to the center of mass. So with that, we can say that Ri is equal to RCM plus Ri prime. And if we can differentiate this and get that Vi be equal to VCM plus Vi prime. All right, so we can go ahead and stick that back in to our definition of angular momentum. So we have L will be equal to sum over I, RCM plus Ri prime crossed with VCM plus Vi prime. All right, so we can distribute away. A little bit of FOIL action here will give us a total of 4 terms. So we will have, oops, I dropped my MI. Much better. Okay, so let's go ahead and do some FOIL action here. I'll have a sum over I, RCM cross MI VCM plus our second term will be sum over I, RCM cross MI VI prime. Our third term will be plus sum over I, Ri prime cross Mi VCM plus sum over I, Ri prime cross Mi Vi prime. Okay, well, we can pull a sum over I from everything, so let's go ahead and do that. So over I, okay, and then we'll just look at, so then we have RCM cross VCM plus RCM cross VI prime plus RI prime cross VCM plus RI prime cross VI prime. Okay, so we'll call this triple star. So the terms we're going to focus our attention on are the center two terms. All right. So we have here sum over I, MI RCM cross VI prime plus sum over I, MI RI prime cross VCM prime. All right, so that equals. Now the first term here, I can go ahead and move the MI over there. Absolutely nothing wrong with it. In fact, what I'm going to do, so we can move the MI over here for what it's worth. And then I can pull the RCM cross out of the sum. So I'll have RCM crossed into, and then I can write this as ddt of, oops, I need my sum over I, MI, RI prime. And I'll do the same sort of thing here. I'll just say that this is sum over I, MI, RI prime. I'll group it, crossed into, and I'll write this as RCM dot. Well then, this term, so in both cases here, let's go look at this one first. This term is, I assert, is equal to 0. Why is that? Pause the video and I'll see you on the other side. Okay, it's 0 because it's locating the center of mass in the center of mass coordinates. So you're locating the center of mass with respect to the center of mass itself, so it's 0. Ditto, the position of the center of mass relative to the center of mass is never going to change. So I'm differentiating 0 here. So both of those middle terms then just plain equal the null vector. Okay, so with that in hand, let's go ahead and see what's happened to triple star now that we've dispensed with the middle two terms. I have L is equal to sum over I, MI, RCM cross VCM plus sum over I, MI, RI prime cross VI prime. All right, well, this bit here, I can pull the RCM cross out. RCM cross sum over I, MI, VCM plus, then over here, I'll just leave it. Sum over I, MI, I'm sorry, I'm going to move the MI over. That's what I was going to do. RI prime cross MI VI prime. Okay, now here I look at this and I realize VCM is just a constant. So that's sum over I of MI, that's just going to give me M. So I get that the angular momentum is RCM cross M VCM plus sum over I RI prime cross MI, whoops, interesting, cross MI VI prime. And that's about as far as we can drill it down. But what we can do is we can look at this and we can say the angular momentum of a system is the angular momentum of a point mass about the origin. So we can kind of call this, that's what this term is, we can call that the orbit, if you will. Plus the angular momentum of the system about its center of mass. We can call that the spin part, if you will. Okay. So next chapter we'll be pushing on that thought a little harder to develop the parallel axis theorem. But this is the beginnings of that. Alrighty then, so let's go ahead and develop the kinetic energy. So I'm just going to do what we've done before. The kinetic energy is equals sum over I. We'll be nice about the first time. Equals 1 to n of 1/2 mi vi squared, which would be sum over I mi times vi dotted with itself. That's how you square something. So again, we can go ahead and expand that out in terms of our center of mass representation. Say it's sum over I of 1/2 mi times VCM plus VI prime. That plus sure looks a lot like a cross. Dotted with VCM plus VI prime. Okay, so let's go ahead and do that. We're going to call this next result quadruple star. So T equals sum over I 1/2 mi. I can pull that out of everything. And again, doing FOIL action here, I'm going to get VCM dotted with itself plus the cross term, so 2VCM dotted with VI prime plus VI prime dotted with itself. And as always, it's the center term that's going to give us the heartburn. So let's follow it through. So that term is going to be sum over I 1/2 mi times 2 VCM dotted with VI prime. All right. Thank God for small favors. Can cancel the 2's. That's actually helpful. Now I can put the mi next to I can first multiply the VI prime by mi. No harm, no foul there. So it becomes sum over I VCM dotted with mi VI prime. Now I can pull the VCM dot out of the sum. So this is VCM dotted with sum over I mi VI prime. Well, to within a factor of the mass, this, which isn't going to matter, this term here gives me the velocity of the center of mass with respect to the center of mass, which is 0. So the cross term is 0. All right, so then quadruple star becomes T equals sum over I 1/2 mi VCM dotted with itself plus sum over I 1/2 mi VI prime dotted with itself. All right, now here I can just go ahead and evaluate this. VCM.VCM is just going to be VCM squared for every single iteration. So I'm left with a sum of mi, which is just m. So that'll be 1/2 mvcm squared. And then this we just this is just going to be vi squared. But the best thing to do is just say sum I equals 1 to n 1/2 mi vi prime squared. All right, so the moral of the story is that the kinetic energy is the kinetic energy due to the translation of the system, of the whole system, plus the kinetic energy of motion relative to the mass center. All right. So I've kept you in suspense long enough. Now's the time to revisit our falling chain. And this time do it right. So this time we're going to go ahead and use energy conservation. So just a quick refresher from the last video. This is my point A. There's my chain. There's my point B. We'll go ahead and say that this distance here is x. So then this here, this distance here will work out to be L plus x over 2. And this distance here will work out to be L minus x over 2. And then, so, whoops, that's probably a little overly optimistic. Let's say maybe somewhere there, that would be my XCM. All right, so some things I can still go ahead and write as before. I can say P dot is equal to mg minus t is equal to lambda over 2 minus, times minus x dot squared plus x double dot L minus x. That part was legit from before. And now let's write our expression for XCM. Actually, I think I'm going to need the whole screen to do that. So XCM equals, the mass will be 1 over lambda L times our two constituent pieces are this guy here. His mass is going to be lambda times L plus x over 2. Right. But it's only halfway down. So this is mass, but then its position is 1/2 of that going halfway down. 1/2 L plus x over 2. And similarly, for the second guy, the mass is lambda times L minus x over 2. And then we will pick up a 1/2 L minus x over 2 plus x. And close the square bracket out over there too somehow. All right. Lambdas cancel. Thank God for small favors. I can pull a 1/2 out of everything. Actually, I can do a lot more than that. I can pull out 1/2, 1/2, 1/2, 1/2, 1/2, 1/2, as long as I go ahead and times that by some stuff. So we'll get 1 over 8L then this will give me an L plus X squared. Then here I'm going to get a L minus X times L minus X plus 4X from there, which will give me, because I had a 4X there to go on the common denominator when I pulled out my 8. So this much will just become L plus 3X right there. All right. So when in doubt, expand it out. 1 over 8L. This will give me L squared plus 2LX plus X squared. And then this will give me L squared plus, let's see, 2LX minus 3X squared. All right. So then that becomes 1 over 8L times 2L squared plus 4LX minus 2X squared. I can drop a factor of 2 everywhere. Again, thank God for small favors. All right, so now that I've got my center of mass, I can say that the potential energy is minus mg times xcm. So this will be minus big M is just minus lambda L g, and then my xcm is going to be 1 over 4L times L squared plus 2LX minus X squared. So cancel there. So it becomes minus lambda over 4 times g times L squared plus 2LX minus X squared. All right. Now for the kinetic energy, the left-hand side isn't moving, but the right-hand side is. So that will be just the mass of the right-hand side, so we'll have a 1/2. Then for the mass, that will be lambda times L minus X over 2. X dot squared. So we get lambda over 4, L minus X, X dot squared. All right, so we can go ahead and do conservation of energy here. T plus V had to equal V naught from back in the day. So we'll just put it all together. Lambda over 4, L minus X times X dot squared minus lambda over 4 times G times L squared plus 2LX minus X squared would have been, back when it was all hung up neatly, minus lambda over 4, just putting in x equals 0 really is all I'm doing here, GL squared. All right, so first off, we can cancel the lambda over 4s. And then this GL squared term here, so this all just goes to 0, cancels that L squared off right to there. So I am left with x dot squared equals g times 2lx minus x squared over L minus x. Alrighty. And I can go ahead and differentiate this with respect to time. So then this will become 2x dot times derivative of what's inside x double dot. That will equal, and this is a bit messy, mg times 2L x dot squared minus 2x x dot over L minus x plus g 2Lx minus x squared over L minus x squared x dot. All right, well, everywhere I can cancel an x dot. That's nice. 2Lx dot. Where'd that rogue square come from? Okay, so I can cancel an x dot there, there, and there. All right. And then I can rearrange just a little bit. I can get x double dot is equal to g plus g times 2lx minus x squared over 2l minus x squared. All right. Now, if we remember from back in the day, P dot was mg minus t. I'm using T two different ways, as tension and as kinetic energy, aren't I? Yeah, let's just call all those K's for the moment, kind of just going back a little more old school. All right. So anyway, mg minus the tension T is going to be lambda over 2 minus x dot squared plus x double dot L minus x. Right? But we just worked out what x double dot was and what we've worked out both x dot and x double dot. So now we can put it in. So we get mg minus t is equal to lambda over 2 times minus g 2lx minus x squared over L minus x plus g L minus x plus g 2lx minus x squared over 2L minus x. All right. And basically now you're just going to have an enormous amount of algebra. The one thing you'll want to do is call this lambda L. It does make life easier. And you get, so after you do about a page of algebra, you get T is equal to mg over 4L times 1 over L minus x times 2L squared plus 2LX minus 3x squared. And if you go look at that journal article that I mentioned before in the previous video, you get that this is the correct expression. Now, or at least experiment agrees well with it. Now let's go and relook at this x double dot term. One of the things you notice here is that the tension is greater, that x double dot is greater than g. So actually the chain is literally getting pulled down. So the tension in the right hand side is unequal to 0, unlike our tacit assumption before that it was. So the results that we get out of this are that x double dot is greater than g. And I also just say you can show, I'm not going to bother here, but you can show that the tension on the left hand side equals tension on the right hand side. So right at that join is equal to lambda x dot squared over 4. Okay, in the next video we will go ahead and explore the reduced mass.